So in this video we're going to take our floating point unit and we're going to design it into our system. Now it's just going to be a lot of me talking and showing the actual circuitry, but in a later video we will go through an actual command and you can see the whole circuitry working. Now I will get rid of my image because it doesn't add any value here and it just is a bit of a distraction. So there were two different methods that I looked into. The first one was to treat the floating point unit as if it's a separate chip. Now in effect this is what happened whenever the first math coprocessors or floating point units, I'll use both of those terms interchangeably. So when those first units were designed, they were designed as separate chips. So for example, the Intel 8087 was a math coprocessor and it was a separate chip that you could buy, and it would talk to the 8088 CPU. Now the other option is to take the floating point unit and integrate it into in effect the same chip, that is the same die as the CPU, which is what would happen with modern CPUs. So let's quickly look at the first option, which was to have the separate chip. So if we head down into the computer, if you right click here and you can see it's the motherboard. So in effect this just looks like the motherboard of any computer. So you would have the chip here, which is the CPU. You would have ROM cards and you would have some RAM as well. And we've also down here got input-output devices. So obviously in an actual motherboard it's a lot more complicated, but we've got the basic structure here of some average motherboard. Now what we could have done is we could have taken one of these spare input-output cards and we could have replaced it with an entire floating point unit. So in effect this card here would be a single chip, so there would be a position in order to drop a chip into the motherboard, and that chip would be our floating point unit. Now I decided against doing that, and now the reason for not doing that is that in order for the CPU to pass the information out into the input-output device, first of all it would have to pass a value for X, and then it would have to pass a value for Y, and then it would have to pass the select line. So the select would choose between whether it's going to be add, subtract, multiply, division or square root in the floating point unit. So it would have to pass all these values over, and then once it passed over it would have to take the value from the card here back onto the bus. So it was going to have to use more clock pulses in order to do that, and it would be a little bit slower and a little bit more cumbersome. So the other option was to actually use the floating point unit as it integrated into a single die along with the CPU. So we have the CPU here. If we drop down in, you can see the floating point unit is actually over here. So within our CPU we've got our ALU, we've got all of our registers, we've got accumulator, instruction address register, instruction register, and a memory address register, and the clock signals here, and the whole control unit. So what we've done is we've stuck this extra block here and it's called the floating point unit. So I'll zoom in a bit so that you can see it a little bit better. Okay, so we've got the floating point unit here. So it looks like it's just it could be a small unit, but it's just a single block here. But this block is far more complicated than all of the other circuitry put together, and probably 2 or 3 times bigger than the rest of the circuitry. So a floating point unit is really quite a complicated bit of equipment. Now we're going to talk through here, and it'll take 10 or 15 minutes just to go through and show you how this has been designed in. Now the first thing to note is the floating point unit is going to have three inputs. So it's going to have an X and a Y, which in effect are going to be floating point numbers that will come into the unit. And then it's going to have a select line, and the select is going to choose add, subtract, multiply, division, or square root. Now there's one other function there which we'll talk about later, but it's not involved at the moment. Okay, so the other part of it is the output. So you'll have an output coming here, and it's simply called out. And then you're going to have these other outputs here, which we'll talk about just in a few minutes. But the main part is you've got an X and a Y coming in. So you get two numbers coming in, and then you're going to either add, subtract, multiply, divide, or you're going to have to find the square root of one of them. Okay, and then this will go to the output. Now the thing about this floating point unit and the way I've designed it is it's purely combinatorial. That is, there's no clock pulses required in order to get the output. So as soon as you put an X and a Y in here and it's selected, then the output appears instantly. Now what I mean by instantly is that in an actual circuit there would obviously be some delay through the combinational circuitry, but it would be very minimal. So this is quite a unique and quite a neat design. Now considering that if you were normally to do a division algorithm, it could take several clock pulses to go through a division algorithm, but this division algorithm is instantaneous. Okay, so we will look at each of the individual parts within the floating point unit, and we'll look at those over the next few videos. But let's just see how this floating point unit is designed into the system. So we're going to have an X and a Y in our output, but where does the X and the Y come from? Well, if we head over here, you can see here that the X and the Y just come from the inputs of the ALU. And then the output here is fed into the input to the accumulator. So in effect, if you think about this X and Y and the output, the floating point unit in effect just sits in parallel with the ALU. So whenever we're using the floating point unit, what happens is that any information or the numbers are going to come out of the register or the memory and come into the value here at Y, and then the other number is going to come out of another register or another memory location, and it's going to head into this point here, at which point we've got a copy of these over in the floating point unit. So they're heading in here and they get into the floating point unit. So the floating point unit is then going to, at some point, will be clocked, but the floating point unit will be selected here by FPU, and the output will appear here. So whenever they get the output appearing there, output is just fed straight into the accumulator via this mux. So you can see that the floating point unit just sits in parallel with the ALU. When the floating point unit is in use, the ALU is not in use, okay? And when the ALU is in use, the floating point unit isn't. So it's that simple, and that's how easy it is to plumb it in. It's just placed in parallel with this ALU. Now, the only part of it that is difficult here is the choice here. So we have to choose whether the output comes from the ALU or the output comes from the floating point unit. And we do this with this FPU line. Okay, so if we head over to the floating point unit, you'll see here that we're going to have the FPU is going to control these little buffers. Okay, now the reason for using these control buffers is that whenever the FPU is low, the control buffers are open circuit, and whenever these are open circuit, it means that Logisim in effect doesn't even recognise that the floating point unit exists. So it doesn't bother going through any calculations or unnecessary calculations. So it's an excellent way to extend the functionality of Logisim. It means we can build even more complicated circuits, and we just connect them via control buffers, and we can just open or close the control buffer and just use the the extra circuit, in this case the floating point unit, when we want it. Okay, now if I didn't do it like this and I didn't use a control buffer, then the floating point unit would always be working and it would slow down the Logisim simulation, so it would be really unusable. So this is a nice, neat little trick in order to employ the floating point unit. So the floating point unit is going to have the select line here, and it's also going to have this FPU E here, and both of these come from the control section. So we want to have a look at those, but before we have a look at those, just a thing to note here is that whenever we're using the floating point unit, it means that the ALU is no longer in use. So if the ALU is no longer in use, it means that the control lines here, which were coming out to pick the functions within the ALU, are now free to be used to choose the functions in the floating point unit instead. So these lines here, these control lines, become available to us whenever the ALU is no longer in use. So whenever we drop down into the control section, the first thing to note is that we have to be able to recognize a floating point unit instruction. So when we generate the instructions, we choose the floating point unit instructions, so we get one after another, and let's say they're in between two particular values. So if the instruction comes in here to the instruction register of the control unit, and if it's a floating point unit instruction, we can test for it here with this little test cell. So this is CPU ALU underscore FPU. So this is testing whether it's a floating point unit instruction or not. And if we drop down in, it's actually a very simple little circuit. It's just a couple of comparators, and then we're comparing between two values, and everything that's between these two values would be a floating point unit instruction, in which case the output would go high. So that's just a simple test to find out whether we have actually got a floating point unit instruction coming into our instruction register or not. Okay, so we'll go back into the control section. Now, if this is a floating point unit instruction, then this line here is going to go high. But that's not the only thing that we want to check. Okay, we want to actually wait until we have the choice of the floating point unit function. So the floating point unit function would be a value 1, 2, 3, 4, 5 for add, subtract, multiply, division and square root. And there's another one, there's a sixth one there which we'll talk about later. So as I said, we are going to have these ALU lines. These are going to be free whenever it's a floating point unit instruction. So that means that we can take a copy of these lines here. So in this case I've taken ALU 0, 1 and 2. So these are going to define the ALU, the floating point unit instruction. So you can see here that I take a value out here, and that's going to be a number. If there's 3 lines, we'll have 2 to the 3, which is 8 different functions that we can choose within the floating point unit. So this output here becomes the select line for the floating point unit. Now another thing we do here is if any one of these values go high, it means that we have made a choice. So we've chosen a particular function within the ALU. So when we drop down here, we've got this line here which says it is a floating point unit function. This line here tells us that we have chosen the actual function within the floating point unit that we want to use. Now there is one other complication, and this is this ALUE. So there is a command which is the floating point comparison, and the floating point comparison is not actually part of the floating point unit. it's still sitting inside the ALU. Okay, now there is another point as well, and this is for something called the fpixel command. So these two commands, there's a little bit of extra complication, okay, because they don't get fulfilled completely within the floating point unit. Okay, part of it is within the ALU still. So we've got this other control line here. So this other control line here is actually an extra line that we've got left over. So we had this extra line left over, and this extra line was originally used for the carry in and carry out circuitry. But we weren't using the carry in, carry out, and I've got rid of it. And it's freed up this extra control line, and we can use this extra control line in order to define whether we're going to use this fcomp or fpixel command. So this is the extra little bit of circuitry. Now, if all three of these are high, then it means that the floating point unit is going to be enabled. So let's go back up to the level above. Okay, so it means that the floating point unit enable has gone high. Okay, so if I'll zoom in a little bit further. So it means that this here has gone high. If this has gone high, it means that we're going to pass the X, the Y, and the select line into the floating point unit. In effect, the floating point unit is now getting used. And we're going to pass the output directly out here. And that output is going to come along and it's going to get passed through the multiplexer because FPU goes high and it chooses this output here. So the floating point unit output now goes into the accumulator and gets passed into the bus. Okay. Now, one other thing to note here, if I go down into the floating point unit, don't worry too much about the connectivity here. We're going to explain this over the next few videos. Okay, but one thing to note is that I do have the flags coming up from the floating point unit, and I had to put in this little, in effect, memory cell or little register, which just contained the value for these flags. Okay, so if I didn't have this, then the flag would just pulse on and off momentarily. But what I wanted to do was I wanted to set the value within this little memory cell, so it stayed on until the next flag came along and the next flag was set. So we ended up with this extra line here, which is a little set line, which is setting the value within this. Okay, so it's just a simple memory cell, which you've seen plenty of times before. So let's head back up to the motherboard. So we can see here that this set here for these special caches, or the flags, is again set by this FPU, and it's going to head through an AND gate, and it's going to be set with a clock set. Okay, so that's the last little part of this floating point unit. So that's the floating point unit completely installed. Now, in the next video, what we can do is we can have a look at an actual floating point unit instruction, and we can watch it going through, for example, an addition. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.